Hello everyone, welcome to the third lecture, I believe, video lecture of COMP3141. Today we'll be talking about testing and how testing can also be a part of our mathematically structured programming approach in Haskell. And in addition to the testing, which will comprise most of this video, I'll also be talking a bit about Haskell's evaluation model and how Haskell programs actually execute on the machine. And this should help you get an intuition for how Haskell programs actually run. Now, the reason I've left it until week 3 to talk about how programs actually execute is that we don't want you to think too much in terms of operational reasoning. And by that I mean, we don't want you to think about what the program does. Instead, we'd rather you thought about what the program is in the sense of mathematics. And the reason we want that distinction is if you do this assertional reasoning, this sort of equational reasoning that we've been doing with our proofs last week, then that's a much better way to think about programs when you want to ensure that they work in all cases. If you think about what the program does, then you'll end up thinking the program first does this, then it does that, then it does the other thing, and you'll inevitably miss corner cases. So we are trying to impress upon you the importance of thinking about things in a more invariant, state abstract way and in a more mathematical way. But because Haskell programs ultimately do execute on a machine, you do need to know a little bit about Haskell programs and how they actually execute. So we'll cover that as well. Okay, so let's get started. Right, so if we're thinking about what sort of properties we want to hold about our program, just by using Haskell or a similar language, we can automatically ensure many properties. One of the most basic properties that a language can ensure for you is memory safety. So that is to say, memory is accessed where and when it is supposed to. So that's two types of memory safety. One is called temporal safety, and that is you don't access memory when you're not supposed to. So for example, if you use memory after a free, that's a violation of temporal safety. And there's also spatial safety, which is you only access the parts of memory that you're supposed to. So if you access outside the bounds of an array, that would be a spatial safety violation. But Haskell's type system and its runtime system automatically ensure that memory safety is satisfied. And Haskell is not the only language which does this. Java, for example, is also memory safe, as are most programming languages in common use today, except for C and C++, which inherits the unsafety from C. There are always escape hatches in many of these languages that let you circumvent some of the memory safety guarantees, but in general, these properties hold. We also have two properties that make up a notion called type safety. If you do my other course, COMP3141, we'll give you a more formal definition of this, but essentially, type safety says that values of a certain static type will actually have that type at runtime, so you can't get values that don't match up to their static types. And also that if you have a program that has been given a well-typed, that is judged to be well-typed by the type checker, then there is no undefined behavior. You cannot get to a state where you can't tell from the language definition what will happen next. And so these two properties together form what's known as type safety. So there are fewer type-safe languages than there are memory-safe languages, but type safety is also pretty common in many modern programming languages around today. The one property that Haskell guarantees that most programming languages do not is that programs will not have side effects that are not declared in their type. So all functions that you write in Haskell are pure. That means if you say a function is a function from an integer to an integer, then if you give it an integer, then the only thing that function can do is return an integer, right? They can't launch missiles or explode or print to the console or communicate with a concurrent process or anything else, right? They can only return the value that return the value they're supposed to compute based on the inputs that they're given, right? And they can't access other inputs beyond the inputs they're given. So they're basically mathematical functions. They take an input and map it to an output. And this is, when you program with functions in this way, it's called purely functional programming. And Haskell is one of the few purely functional programming languages that exist, and is certainly the most popular one. So because our language, Haskell, guarantees all four of these properties, then most of the properties that we have to test or prove about our programs are about the logic of our program, the actual business logic we're trying to implement. We don't need to worry about proving or establishing that memory safety is guaranteed, because that's an ambient property that's given to us by the language itself. So if we're talking about properties, logical properties by which I mean properties pertaining to the business logic of our program, then we've already seen a few examples of these. And they come in the form of type class laws, as well as some of the properties that Curtis would have proven in his previous lecture. So I believe Curtis proved that reverse is an involution. That is, if you reverse a list twice, you'll get back the same list. And then the type class law for plus plus, the right identity of plus plus, x's plus the empty list is x's. And transitivity of greater than even is another example of a logical property. So if we can come up with a set of properties that together guarantee, together state exactly what we want our program to do and exactly what we don't want our program to do, right? So then that set of properties would be the definition of correctness for our program, right? If I can come up with a set of properties that specify every requirement of my program, including the things that I don't want it to do, as well as the things I do want it to do, then that would guarantee any program that implements that spec will be satisfactory for my requirements. And so that set of properties is called the functional correctness specification. It's just the definition of correctness for a piece of software. So last week, both in my video and in Curtis's lecture, we saw some proof methods for Haskell programs. So we can use this equational reasoning approach to show that two terms are equivalent, and then we can also use induction on data types to show that programs work for all possible inputs. So these proofs are very good at guaranteeing a very high degree of assurance. And a lot of the tedium that you may have noticed when Curtis was doing his proofs, they sometimes took pretty long, can be reduced, not eliminated, but reduced by using machine-assisted proof assistants like Isabelle. And if you want to learn about how to use those tools, the course COMP3141 is all about that. So we can use these machine-assisted proof assistants to reduce the tedium of this proof method, and then thereby gain a great deal of confidence in the result of our proof. Because if we have a machine-assisted proof, it can check the proof for us, so it's nearly impossible to make a mistake, and we can reduce the tedium. And so therefore we can guarantee that the software that we have proven the property about definitely satisfies that property. However, and this is a big however, if you look at any of the published academic results about formal verification of software, including the very famous formally verified microkernel SEL4, which many people here at UNSW work on, there's always an asterisk when they say, we proved that this program was correct. Because all proofs will have to make some degree of assumption about the environment of the software, like what computer it is executing on, and what assumptions about the hardware you have to make, things like that, as well as the semantics of the programming language in which it was implemented. So SEL4, for example, which was proven correct against a functional correctness specification, was implemented in C. And there's no mathematical definition of what a C program means. So in order to prove it correct, they had to define what a C program means in terms of mathematics. And doing that is not necessarily an error-free process. So it's possible that there could be errors in the semantics they assigned to the programming language, as well as assumptions that are not true in the environment in which the operating system is running. So these proofs definitely reduce the likelihood of bugs more than any other method, but they do still have assumptions. And indeed, it has been noted that you do still sometimes occasionally find the odd bug or two in formally verified software. So they're not completely foolproof. Not only that, but as we saw, reverse is a 2-line function, but it took Curtis, I don't remember exactly, but maybe it was about half an hour to prove that reverse is an involution, right? And if you can imagine you had a 8-line function or a 10-line function, I know Haskell functions are pretty small, but even if you had an 8 or 10-line function, the proof complexity would grow superlinearly at least with respect to the size of the implementation. As my implementation gets bigger, the proof also gets bigger. And usually it gets bigger faster than the implementation does. So we get to a point where, without machine assistance at least, it is completely impractical to do proofs on large software systems. And even with machine assistance, it's a lot of work. And another problem with proof methods is that if the software is incorrect, right? So we're not perfect programmers. We might have written a bug. If we try to then prove that incorrect program correct, we may not just find a counterexample to help us debug our program. We might just get stuck trying to prove it and just not get anywhere. And if you get stuck trying to prove a program correct, that doesn't mean that the program is incorrect. It just means you haven't found a proof that it's correct. There may be some other method or some other mathematics you could use to prove it correct, and you just don't know what that is. So you can't tell, if you can't prove it correct, whether or not the problem is in the program or if the problem is in your brain. So this is another issue with formal proof methods. Proofs can also be quite labor intensive and time intensive. I mean, we saw how long it took to do those basic proofs last week. Or it can require highly specialized knowledge. Depending on the system you're trying to verify and the properties you're trying to prove, it can be quite tricky and involve some serious mathematics in order to be able to do these proofs. So how does testing compare to proofs? Well, testing is clearly, I think pretty uncontroversially, gives you a lesser degree of assurance than proofs do. If you test a piece of software, that is a much weaker guarantee of correctness than a proof is. However, tests do usually run in the actual environment in which the software will execute. Or even if not, it will at least be running. Right? When we did our proof, we would manually evaluate Haskell programs using equational reasoning. But there's no guarantee that Haskell semantics actually work that way. So our proof relies on the fact that Haskell and the Haskell execution environment will execute in such a way that is equivalent to our equational reasoning. But with a test, we are just running the program on a computer, so the programming language semantics, at least, will be the same semantics that are used for the test. So we will always be able to keep those matching up. So we don't need as many assumptions about the operating environment of the program as we do in proofs. That said, we do still sometimes need some assumptions because, for example, you're not usually running your tests on the same exact environment as you actually run the program. test complexity, if you do black box specification-based testing, which is what we'll be doing in this course, the tests typically do not grow with implementation complexity at all. You will just specify the relationship between your desired inputs and desired outputs, and if you do some refactoring that doesn't change the interface, that drastically increases the size of your code, maybe for efficiency reasons, that's not going to change the complexity of your tests one bit. Your tests just check that the output is the correct output given the given inputs. So tests do not get worse as your implementation gets more complicated, unlike proofs. And if you test incorrect software and the testing finds the bug, which is a big if, but if the testing does find the bug in the incorrect software, then you have a counterexample, and you can run that with a debugger. You can find out why the program isn't working the way you expect. And typically, it's a lot cheaper and faster than proving, because you're just writing some tests, you're just writing what you expect. You don't need to use specialized knowledge. You don't need to go to the effort of stepping through your implementation or anything like that. On the other hand, tests have to care about efficiency, for example. If I have a proof that my program, if I had a proof that my program returns a prime number, testing that my program returns a prime number would require me to compute primality, which is not necessarily a cheap algorithm. So we sometimes have to care about computation when we're doing our proof. And sometimes we'd even have to care about computability. So it's possible, for example, termination is a common property that we might want to show about a program, that the program actually returns given any input. And we can prove that property. There's techniques for doing that. So we could prove that a program terminates, but we can't compute if a program terminates. It's a well-known famous problem called the halting problem. And so we can't really write a test to test if a program terminates. We can try to approximate it, but we can't really get there. So we have to care about computability as well. So tests sacrifice a great deal of assurance, and we do have to care about the performance of our tests and the computability of our tests, but we do gain a lot of convenience. And convenience here is just another word for money. So how are we going to tie in the notion of testing with the kind of mathematically structured specificational reasoning that we're doing in this course? What we'll do is a technique called property-based testing. So the key idea here is we write a Haskell function. Here it's called prop reverse app, and it takes in two lists, and it states that reverse of x's plus y's is equal to reverse of y's plus reverse of x's, right? And this is a true property of any two lists, and the function reverse. And it will just generate a bunch of random input values and test the property by running that function. And if the function returns true for all of the random input values it generated, we consider the function to have passed the tests. So I'm going to demonstrate this now, just briefly. Let's move over to, hold on, here we go. So I'll just edit a file. So I'm going to import the library called QuickCheck, which is Haskell's property-based testing library. And I'm going to write my reverse app property, x's, y's, and the type of it is just taking in a list of integers, let's say, and another list of integers, and returning a boolean. And the property is reverse of x's plus y's equals reverse of y's plus reverse of x's. Very good. Okay, so now I should try to save that, load it up. Okay, it works. And now if I call the function QuickCheck, I'll show you the type. Right now this won't make a lot of sense, but I'll explain what all of this means in a moment. I need to give it a testable thing. That's the main thing we can see from this. And this prop reverse app function that I just wrote is an example of such a testable thing. So I'll pass it into QuickCheck and it will run 100 tests. I can run many more. And let's suppose I made my property incorrect. Suppose I said this instead. I changed it to x's plus y's, or instead of y's plus x's. Then if I try my property, it says, nah, failed. And here is a counterexample. For x's, I gave you the list containing the number 0. And for y's, I gave you the list containing the number 1. Right? So here's an example of two lists for which this property returns false. So it actually tells you that. Okay, so let's fix that before I forget. It was actually y's plus x's. Very good. Okay, so that's a quick demo of Haskell's QuickCheck library, but there are actually many other libraries for this in many languages, and they have different design decisions and different testing approaches and stuff. And some of them are very powerful and do very interesting things. So I encourage you to explore the full range of property-based testing libraries. But in this course, we'll just be using QuickCheck. If you use any of the listed languages here, so Erlang, Scheme, Common Lisp, Perl, Python, Ruby, Java, Scala, F#, OCaml, Standard MLC, and C++, I know of property-based testing libraries for those. Oh, I also know there's one for JavaScript and the web document object model as well. That's actually quite cool. It uses temporal logic to do properties. So if you're interested in any of those, let me know and I'll point you to the right place to look. But in this course, we'll just be using QuickCheck, but the stuff you learn from doing QuickCheck testing, you will be able to apply in any of these languages using their property-based testing libraries as well. So let's compare property-based testing, what I just did there, where it generated a bunch of random inputs to my function, with unit testing, where we hand select a few artisanal proof cases to run through our program, or rather test cases, not proof cases, to run through our program and check if they work, right? So if we look at properties, well, it's a lot more compact than unit tests, right? I described 100 test cases, randomly generated test cases, in one line, right? Just by describing my property. There's a much less testing code compared to unit testing. However, property-based testing does heavily depend on how we generate data. So I just said it's randomly generated. We'll see a bit more about how that works in a moment. And there are other property-based testing libraries that do other types of generation than QuickCheck does, which are a bit less random and a bit more selective. But effectively, we do heavily depend on this generation process, and this comes with a few problems. So the first problem is that if we just generate a random input, say we have a function that takes in integer inputs, if we were hand selecting our test cases, we'd probably pick, okay, 0, because that's a good edge case, maybe -1, and then like -10, and +1, +5, and 10. Maybe that's a decent set. And maybe a big number like 1 billion or something like that. So we would pick numbers that try to cover every possible equivalence class of inputs and then run them through our program. But property-based testing is just going to randomly pick a number. So let's suppose that our program was broken for all numbers that were anything bigger than 10. But QuickCheck decided it's going to pick 4.2 billion. Well, okay, that is a number that it fails on, but it would be much easier to work with if we had a number just like 10 instead of 4.2 billion, right? So there is a feature in QuickCheck, and we saw it in our example actually, called shrinking. And what that means is whenever an input fails a particular test property, then it will try to minimize that failure to a smaller example. And we'll show you how that works in a moment. But even if we just go back to our example here, if I go back to my code, it says falsified after 5 tests. So it tried 5 cases, and on the 5th case it failed, and 5 shrinks. So it failed, and then it shrunk down that test case to the smallest possible test case it could find that still failed the property, right? So this helps to simplify our failures so we don't get weird inputs to our function. We get the smallest possible inputs to our function that still fail. So that makes it a bit easier to work with. So that sort of addresses that problem. But still, random inputs are not quite as informative as handcrafted inputs. And then, well, there's always the problem in testing that you may not cover all the cases that you need to cover, right? And just as with unit testing, you can forget to put in certain cases. With random testing, we may not cover all of the necessary cases that we should. So an easy way to check if this is the case is to use a coverage checker. Now, last year when I taught this course, and I asked if anyone had seen a coverage checker before, no one raised their hand, and this was very alarming to me. I'm very surprised by that. So I'm hoping this year is different, but of course, being in the video, I can't tell. So what a coverage checker essentially does is check that all of the possible code paths of your, well, not code paths, but all of the possible executions of bits of code, all of the bits of code in your program are exercised by your tests. So if I write 10 test cases, or if I have my random generator generate 100 test cases, and then I check my program and it never executed this one line of code, that tells me, well, that line hasn't been tested. So I need to come up with a way to test that specific line of code that has not been covered already by my existing tests. So yes, it's possible that random inputs may not cover all necessary corner cases, and we might see some examples of that in the future. But this is also true of unit testing, and we need to use coverage checkers to get an idea of how thorough our testing is. Also, for our user-defined types, if we defined our own data types using the data keyword, then QuickCheck doesn't know by default how to generate those, right? So we need to be able to custom generate our own types as well. And QuickCheck includes a bunch of functions and type class machinery to do that. In fact, I believe it's even possible in some cases to derive these generators automatically, although don't quote me on that. But we won't go into too much detail on how that works in this lecture. That will become a bit clearer later on as we talk about some of the more advanced abstractions in Haskell. But for now, we can rely on the fact that QuickCheck already includes generators for all of the basic types that we've seen, like tuples and integers and lists and so on. So each time so one of the coolest things about this is that whenever we increase this number of random test cases to generate, we automatically improve the coverage of our code just by turning up a dial, right? When you're doing unit tests, you have to come up with more test cases, but with property-based testing, you just turn up a number. So that's really nice property. Okay, so I mentioned before about shrinking. So all of the possible data that you can generate randomly as inputs to your test cases are represented by this type class called arbitrary. So arbitrary has 2 methods in it, or 2 functions that you have to implement in order to be an instance of the type class arbitrary. So one is called arbitrary, lowercase, and this returns a generator of A's. And I won't tell you what a generator is now, but just suffice to say that it is a procedure for producing A's randomly, right? And we'll talk about that later on in the course. And it also has this function shrink, right? And shrink is given a right, given a value of our test data, this is a value that has failed a test case. So give me smaller values in this list, in this return list, that could still possibly fail the test case. So what happens is QuickCheck will use this, pardon me, use this arbitrary generator to produce a bunch of inputs, and if any of them fail, it will use this shrink function to get a list of smaller inputs and try all of those. And if any of them fail, it will continue to shrink and shrink and shrink and so on until finally it gets the smallest case it can. So most of these types have implemented arbitrary already, tuples, integers, lists, and so on. So most of the functions that we've been working with so far, you can prove correct, or you can test for correctness using QuickCheck just out of the box. So this QuickCheck function that I used to test my property has this interesting looking type. Now it takes in a testable A, whatever type A is, it just has to be a testable thing, and returns an IO action. Now I'll tell you what an IO action is in week 5, I think. I want to say week 5. But suffice to say for now, it's just a command that can maybe print to the screen or do some testing or do some side effects to have some effect on the outside world. So what it will do is generate a bunch of random test cases and print the results to the screen, as we saw in our example. So the main thing that we care about here is the input to this function, which is the testable object A. So this testable type class is the type class of things that can be converted into properties, right? So booleans by themselves are properties, or if the boolean is true, then the property holds, and if the boolean is false, then the property doesn't hold, right? QuickCheck has a built-in property type as well, which is essentially a boolean. It's a boolean with some extra features, and I'll talk about what that is later, but you can think of it as much like a boolean. And then, in addition to booleans and souped-up booleans, any function from an arbitrary input to a testable output, like one of these or another one of these functions, is itself testable. So, for example, if we look at my code here, this is of type int to bool, right? If I put the parentheses in, it looks like that. The bool is testable, right? We know that that's testable because of the property of the definition. And then it takes a list of integers, which is arbitrary, right? So this is arbitrary. I'll just put some space to make that clear. And this is testable. And so overall, this thing is testable too, right? The function itself is testable. And this is arbitrary. Sorry, I just need to adjust my spaces. So we have another arbitrary to testable function. So overall, this thing is testable. That's why I can pass the prop reverse app function directly, without any arguments, straight into the QuickCheck function, and it will generate random inputs to this function to test my property. Right? So this is how the arbitrary and testable type classes work. Now I haven't told you how testable is implemented. It's sort of not important. QuickCheck handles testable for you. You don't really need to define your own instances of testable. The only one you need to define yourself is arbitrary sometimes. So these are the only instances that actually matter to us for testable. Okay, very good. So thus, this type is testable, as I showed you. So now let's try to do some more testing, just with another example here. I've got this divisible function here, and this reflexivity property that says that x should be divisible by itself. And this is true for at least most numbers. So let's try it out in our code here. So divisible xy says x mod y is 0. And prop reflexive takes in a x, which is an arbitrary integer, and says that it's divisible by itself. Okay. Now, that's that. Now, if I try to run QuickCheck on my reflexivity property for divisibility, explode. We get a divide by 0 after one test, so the very first test it tried. And it always seems to be trying 0 first, but that does just seem to be a coincidence. So this is no good. This property is too general. We want to exclude the numbers that are 0, and even probably the negative numbers too, because we don't want to deal with negative modulo spaces. So let's just talk about positive numbers, by which I mean greater than 0. We could try a hack like this to just like get around the fact that x could be 0 by adding 1 to it, but of course this will just give us an error. Oh, okay, here we go. We've got an example of how randomness can be flaky. It actually managed to pass 100 tests the first time, but now reliably seems to fail. So you've got to be careful when we test our programs that we are actually covering all of the cases. You can see it's a very variable number of tests that are running before it actually finds the error. But now that we're adding 1, it's just -1 that causes the problem instead of 0. So this is also no good. So what we need to do is, if x is if x is greater than 0, then we want to check if divisible x by x. But otherwise, we don't care. We don't want to worry about those cases. So one way to do this would be to write something like this. If x is greater than 0, then return this. Otherwise, just I don't know. Just I don't care. It's true, right? This is one way to do it. And if I check that, well, it's always going to pass now, right? Because I'm only putting in positive numbers to my divisible function. But the problem is, I don't know how many of these 100 tests actually tested my divisible function, and how many of them were negative or 0, right? It's not sufficient to say that all negative and 0 numbers just pass the test straight away. That's not good enough. What I want to do is discard any cases that have negative or 0 numbers. So this is where Haskell's QuickCheck's property type comes in. So right now, this is of type integer to bool, or int to bool. The differences between integer and int, integer is unbounded, whereas int is a machine integer. But the difference is irrelevant for this example. So we have int here, and right now it's int to bool, right? That's our prop refl. But what I want to do is discard any cases where x is not positive. So what I'll do is I use this arrow notation, like this. This arrow notation, this equals greater than arrow, is defined by QuickCheck. It's an operator, and it returns a property, right? So what this does, as I said before, property is essentially like Boolean, but it allows us to throw out certain cases, for example. So it says here, if x is greater than 0, then check divisible x by x, otherwise throw out the test case, right? And we can check this like this. As you can see, now it's passing 100 test cases, and additionally, in addition to that 100 that it tried, 117 were thrown out, right? And those thrown out test cases are the ones that failed the precondition that I put on my test case. Okay. That's cool. So, yep, one way to encode our precondition is with that operator. But the downside of this is, if this precondition was hard to satisfy, let's just suppose I made it unreasonably strong. Instead, I changed it to like 1,000. Well, let's hope that QuickCheck generates some big numbers, right? Let's just see what happens. Wow. Okay, so it's probably the fact that the default generator for integers doesn't generate very large numbers, because it does look like it's discarding all possible inputs. So when you see this gave up message, that's bad news. That means your preconditions are too strong, and QuickCheck can't find any inputs that satisfy the precondition. Or can't find enough inputs to satisfy the precondition. So That's not good. So what could we do instead of having a precondition that throws out test cases? Well, we could just generate better test cases. And so QuickCheck uses this new type trick. I talked about this last lecture, where it changes the arbitrary instance for a particular type by defining a new type that wraps around it. And I'll show you what this looks like in the documentation. Let me just get it up. Check test.quickcheck.modifiers, and I'll bring it over to my screen in just a moment. Here we go. Let me just do that. Apologies for the delay. Here we go. So there's this great set of built-in modifiers, and you can also define your own if you know how to make generators, which we'll talk about later. And it includes non-negative, ordered for lists, several others. You can talk about the size of the things you want, positive. That sounds like something we'll want very soon. Negative, non-zero, non-positive, large, small, strings containing only ASCII, and so on and so on. And other modifiers to change how they shrink and so on. So there's all sorts of modifiers in this library here. So let's use some of them. In particular, I want to use the positive modifier here. And this does change the type. Let me check the documentation again to make sure I'm doing this right. Where's positive? Positive A. And it contains an A. And it just requires that that A is num. So we'll just say it takes a positive int, which is a new type around an int. And it has a different arbitrary instance that will always produce positive numbers. So now if I run that with my tests, it doesn't like it. Couldn't match property with type bool. All right. Now that we don't have our precondition, we can change this back to bool. So now if I run it, it passes 100 tests very quickly. It doesn't have to discard any because we are only generating positive numbers. We're never generating 0. Okay, good. Back to the code, not back to the slides. Yep, over here. Okay. So in addition to trying to encode our preconditions with that operator, we can select different generators with these new types. So let's look at these two functions. We've seen at least one of these functions before. I believe we've actually seen both. Words and unwords. Words breaks a string apart into the component words, and unwords does the opposite. It stitches them back together. So we might expect that these two functions are inverses, right? If I do words and then unwords, or words or unwords and then words, then I'll get back the same result. So let's try that, experiment a bit with QuickCheck to see if that's true. So typically the convention is when you're writing a function that is a QuickCheck property, you prefix it with prop underscore, but that's up to you. You don't actually have to do that. It's just a convention. So words unwords is the first property I want to write. And I'm not going to write a type signature here because words, if I call words on my input list or my input string, that's already fixed the type of S because words has a known type. But if you wanted to be clear, you could write the type signature. I am just being lazy. So if I go words and then unwords, then I expect that to be S, right? And similarly, let's also do the other one. Words of unwords, and this isn't a string, it's a list, so I'll rename it to L. So we stitch all of the words together and then split them apart again. We should get back the same list. So these are the two properties I expect to hold. Let's see if they do. QuickCheck. Words unwords. Oh, wait, it's prop words unwords. Nope, doesn't work. So this one doesn't work on the space character. We can see why. If I go words of space, that's the empty list, and then unwords of the empty list is the empty string, which is not equal to the space. So that doesn't work. That's a shame. what about, well, maybe the other direction works, right? Yeah, maybe it was just bad luck in that direction. Well, no, that doesn't work either, because if I take the unwords, I think I gave these names backwards. If I take the unwords of this thing and then words of that, yeah, I did. I named these backwards, but it's okay. I'll fix it in a moment. Then I get back the empty list rather than the list with an empty string. So this is a bit tricky. Well, I'm going to flip the names because this is confusing me otherwise. There we go. Okay, so for this one, where we take a list and we then stitch it back up and split it apart again, we saw that when we had the empty string as one of the words, it didn't work. So what if we just rule those ones out? So if any of the strings in L are equal to the empty string, or actually let's write it this way: if all of the strings in L are not equal to the empty string, then this should hold, right? Because that way we rule out that failing case. Well, let's see if that helps. Oh wait, wrong property. This one. Nope, now it fails for the string that contains a space. And you can imagine if I tried to rule out that one as well, it would just say 2 spaces, right? So what can we do now? Well, how about we say if all of the things, all of the words contain not, or all of the characters inside each string, inside each word, are not space characters, right? And I'll just import data.char for the isSpace function, and that returns true for new lines as well as for spaces and tabs and so on. So I used all twice here. So this is basically saying none of the words in our list can be can contain spaces of any kind, right? Let's see if that works. All right, that doesn't handle the empty list. So, how about this one? It is not the case that any of the characters are space. Let's see if that works. Let's check. Right, so it says none of those are, yeah, right. So that was an equivalent formulation. So I guess we have to do both. We have to say, given a word, all of them are not spaces, and the word is not empty. That's a bit long, a bit ugly, but there we go. So I put this big long precondition on my thing, and let's see if that works. Well, it does pass a lot of tests, passes 68, 66, but it's discarding a hell of a lot as well, because it happens to generate quite a lot of spaces. Still, after running this so many times, we can be pretty confident that it is correct. Now, adjusting this property, the other one, is a little trickier, so I leave that as an exercise for you if you want to try and figure that one out. So yes, words and unwords turn out not to be precisely inverses of each other. So properties aren't always what we expect. But QuickCheck can be useful to discover properties like this. We can test them out and see how they go. Okay, So let's do a bit more of an involved example. So we've all familiar, I hope, with Mergesort, the algorithm to sort lists. It essentially works in a divide and conquer strategy by splitting a list in half, sorting each side, and then merging the two sorted sides. So there's 3 steps: split the list, recursively sort, and then merge. So let's do our bottom-up design approach and posit that we'll have split function that is given the list and returns the 2 halves, or 2 halves of the list, and then merge, which will assume that they're ordered in some way, take the 2 lists and put them together in an ordering. So split is the first function that we need to implement. So what's a good specification of split? Remember that we want our specification to capture everything we want this function to do and everything we want our function not to do. So we want to say that each element of the list that we're given as input, right, this input list of A's here, each of those elements should show up in one of these 2 lists that we return, right? So that's the main thing that we want it to do. But we also don't want it to add any other elements, right? So in addition, the 2 output lists should only consist of elements that come from the input list. So this is essentially saying that these 2 output lists, if I put them together, should be some permutation of my input, right? So let's define a permutation predicate in Haskell. So what does it mean? Permutation, given 2 lists, how could we check if they are a permutation? So there's a cheap way, a kind of trivial way almost, and that is to sort the 2 lists and check if they are equal. And that would tell you if 2 lists are a permutation. It is kind of strange to use sort while testing Mergesort. So if this doesn't please you, an equivalent definition would be permutation x's y's takes in an arbitrary element x and says that the number of x's in x's should be equal to the number of x in y's for any arbitrary x. And this is where count x in the list is the length of filter equal to x in L, right? So this is just the number of x's that occur in L, the number of times x occurs in L, and we say for any arbitrary element x that the number of times x occurs in x's should be the same in y's. And these 2 definitions are basically equivalent. In terms of types, they are not equivalent, so let's write out the type here. We have permutation takes in a list of A and a list of A and a list returns a boolean. And because permutation is using sort, it requires that they're ordered, right? Ord A. Whereas this permutation, which I'll call permutation prime, takes in a list of A, and it only requires that they are comparable for equality. It doesn't require that they're necessarily ordered, and returns a boolean. Oh, wait, no. It actually takes in an arbitrary element A and returns a boolean. So this function here, if we look at this, it is a testable instance, right? Just like bool is a testable instance, so is A to bool. And that's how I can take in this arbitrary value x. So we can use either of these in terms of QuickCheck, and it will be able to convert either one into a property. So the property we want for split, let's do some test-driven development here. We take in our list of A's and return a tuple containing a list of A and another list of A. I'm going to leave the implementation blank, but we're going to write our properties first. This is test first, right? So we're going to write our properties. Our property of split, the first one we had, was that each element of the list should occur in one of the two output lists, and conversely, the two output lists should only consist of elements from the input. So that's just saying permutation. So we've got our list here. If I split, let the left and the right be the split of x's. And I'll just call this the prop split perm, right? It's a permutation. So we split the two in half, and then we say permutation of x's and L plus plus r, right? So L plus plus r should be a permutation of x's. And the exact type of this depends on which permutation we use. Right now we're using the sort one, and we'll see how that goes once we implement split. And I'll also try out the one with the arbitrary x, and we'll see how that's limited in some sense. So we'll get to that. So now that we've got our properties, we can do the test-driven development thing, and wait, it's not going to compile with the whole, so I'll just write undefined. And we can run our QuickCheck property. And of course it's going to fail because we haven't implemented it yet. So now let's implement it. We've got a base case, obviously, and a base case is clearly going to just return a tuple, but what should be in there? Well, we have no elements, so let's just return the empty list on both sides. If we're splitting a list containing A, just one element, then where should we put each element? Well, I guess we should just put A on the left side, just arbitrarily. It doesn't really matter, we can just pick a side. Now, if we have more than two or more elements, then I'm going to first take the left and the right from splitting the rest of my list, and then I'm going to put x on the left and y on the right. Okay, so that's my implementation of split. Now let's actually add a bug here. So when you get one element left in the list, it will return the list element on both sides, so it'll duplicate one element. So this is a bug. Let's just put a comment here to remind me that I put in a bug. And let's see if our function catches the bug. So, yep. Oh, so you might see this looks a bit strange. It's saying list of unit. That's a bit of a weird type. And this is because I was lazy and I didn't put my type signature in. So the problem is GHCI, as we've seen before, it likes to make these defaulting decisions. So when it sees an arbitrary value type that it doesn't know that is of instance of type class arbitrary, it will just pick unit, which is the simplest type you can imagine. It's just data unit equals unit, like that. So that's not a very useful type for us to test things with, particularly if we're sorting lists. If we sort a list of unit, then no matter what order we put it in, it's going to be sorted because there's only one value of type unit. So let's put in a type signature somewhere in our property that says that we expect our list here to be a list of integers. So I didn't put in a full type signature, I just added an annotation to give QuickCheck the hint that I expect a list of integers. Now it gives me a list of integers, and it's still false because it found the bug. Great, it found the bug. Let's see if it still finds the bug when I use my other permutation definition. So now what it's going to do is, instead of sorting the two lists and checking if they're equal, it's going to generate an arbitrary element and count if the number of occurrences of that element in both lists and see if they're equal, right? So if it generates all possible arbitrary elements, then this should be equivalent. But sort, in one test case, will test whether the entire list is a permutation, whereas permutation prime here will just check if the number of one element is the same in each test case. So in order to run, if we had a 100 element list that we were splitting, you'd need to run the permutation prime test case 100 times to even come close to guaranteeing what the permutation what the regular permutation property would give you. But it might still find the bug. It did find the bug, but a little bit, it was less able to shrink it, right? So it does sometimes find it. Oh, here we go. And in this case, it didn't find it at all, right? It didn't find the bug. So this particular implementation, it's still a definition of permutation, but it's not quite as good a one because it leads to flaky tests. So we can avoid the flaky tests just by using sort in our definition. Of course, you can also write your own permutation function that doesn't rely on sorting, but still checks the occurrences of all possible elements. It's just a bit slow. So in any event, we've got our permutation definition. It doesn't really matter how we define it. We could even quick check to see if these two definitions are equivalent, right? I'll leave that as an exercise. So we've specified split in terms of permutation. The only other thing that we might want to specify about split is that the two output lists are half the size of the input list, but this isn't actually necessary for the correctness of merge sort. The only thing that is necessary to prove partial correctness of merge sort is that split is a permutation. And to prove total correctness, that is that it terminates as well, you just need one of the lists to be a bit smaller. And that's all you need. So in terms of program correctness, and not in terms of efficiency, it doesn't actually matter that split actually splits it down the middle or splits the lists into two equal size sublists. It just matters that it splits it at all, right? That it is a permutation. Okay, so now what about merge? So one property of merge is almost the opposite of the property of split, right? Every element in the output list should occur in one of the input lists, right? Either the left-hand or the right-hand one. And the same number of times, of course. And equivalently, everything in the input list should also show up, anything in either of the input lists should show up in the output list the same number of times. So that is essentially permutation once again. So we can just use our permutation predicate for that. And then there's an additional requirement in the implementation of merge, right? We can't just append the two input lists, because that would satisfy the first two properties, but it wouldn't satisfy the third property that we need for the correctness of merge sort. And that is, if the two input lists are sorted, then the output list should be sorted as well. So that's what we're going to try to specify. So let's write our type signature first. Merge takes in two lists of ordered elements and returns a list of ordered elements. It's going to take in our left and right, and for now I'll leave the implementation blank. Let's write our spec. So we have the permutation property that merge should return a permutation of its inputs. So we just need to say permutation of x's plus y's, which is our inputs, and merge of x's and y's, right? This should be a permutation. And just to avoid that unit problem again, I'm going to just chuck a little type signature here, list of integers. And that way it will know that I mean list of integers throughout the property. Okay, and now we want the merge sorted property. So this requires us to say if the two input lists are sorted, then the output list is sorted, right? So we could just encode that directly using a precondition. We could say sorted x's, sorted y's, like that. You can nest these arrows and it works right associatively, just like the function arrow. And then sorted merge x's, y's. And that's a very clear way of writing it. You could also change this implication to an and, right? and that's equivalent. And we'd still have to write our sorted predicate. So sorted, we could cheat and just say that it's x's equals sort x's. But let's not do that. Let's do it properly. The empty list is sorted, right? So let's say that's true. If I have one element, that's also sorted. If I have two elements, then if x is less than or equal to y, right, my first two elements, one is less than or equal to the other, then we're still okay. We just need to check if y and the rest is also sorted. If otherwise, we return false. So an easier way to write that would be, this is true if x is less than or equal to y and sorted of the rest, right? And that way, because of lazy evaluation or short circuiting, it will return false immediately if x is less than or equal to y and not recurse into the rest of the list. So sorted is our little predicate here for any ordered A to bool. So now we could use this. We can go with that, and then we'll try to improve this property a bit later. So how do we merge two lists? Let's start with the most obvious of base cases, and we'll see if we get redundant equations in a moment. We'll go like that. Two empty lists. It's going to produce an empty list, no problem. Now if I have one empty list and a list on the other side, then if I'm merging these two elements, that means I've run out of elements on the first list. So I'll just return the rest of the other list. And similarly, if I run out of elements on the right-hand side. So we can see that this first equation is a special case of both of these second equations. So we can get rid of the first equation. Now we have the actually interesting case. We know that neither of the lists are empty because we've handled both of those cases. So now we have an x and a y, and we want to decide which one of these should come first in our output list. Well, we'll just say if x is less than or equal to y, then x is going to come first, so we'll put x in first, and then the result of merging x's with the remaining y's. And otherwise, I'll just space this to line it up, make it look nice and neat. We'll put y in front and merge x and x's with the remaining y's. Okay, so there's our merge implementation, and we've also got a spec for it, so I think we are ready to try and test it. Merge perm, pass 100 tests, very nice. Merge sorted, pass 100 tests, pass 100 tests. Well, that's interesting. Oh, I know why this is passing so much. Once again, it's because of our terrible unit defaulting problem. Because I didn't specify the type of this list anywhere in this property, Haskell is picking unit, which means that all of these lists that QuickCheck is generating is automatically sorted because they all contain just one element. So let's indicate here that I meant list of integer please. I hate the way it does that defaulting. I think it's a really terrible design decision, but it's my one major gripe with this programming language. Okay, so now it's giving up after passing only a handful of tests. And most of these tests, I would wager, are probably really simple sorted lists, like empty list or a list containing only one element. So we're discarding a hell of a lot of tests, and we're not really making much progress in our testing. So what we want to do is, instead of using this precondition, which is too strong, we want to change this precondition and instead use a new type generator. So if I go back to the documentation, I have, I believe it's called ordered list. Yes, we have this ordered constructor here. So if I use that, ordered of x's and ordered of y's, then I know automatically that this list is sorted. So I can get rid of the precondition. And now, if I go back to my code, it's only generating sorted lists. Now, I'll take a peek because I'm curious. if I look at the source code of this, okay, yeah, but what's going on? Arbitrary ordered list is ordered fmap ordered list, where ordered list is, where is it? Here. So it's using fmap, which we've seen on the arbitrary generator for lists. So it's taking a generator of lists and running the sort function, the built-in sort function, over any arbitrary generated list. So the way it generates sorted lists is to just sort any random old list, right? Which is a perfectly adequate way to do it, I suppose. So we've now specified split and merge, right? So if we look at our code, we've got split, we've got merge, and we've tested them very thoroughly. If we manage to prove these four properties, or three properties that we have, split perm, and merge sorted, then we would have actually proven that these functions are correct. So the fact that we tested these properties gives us a pretty high degree of confidence that we have a correct implementation on our hands. So with this correct implementation, or hopefully correct implementation, let's put it all together and create merge sort. So what's a specification of merge sort? Well, let's write it out. We have merge sort is going to take in a list of orderable things and sort them, returning the same type. Implementation is blank for now. Our spec is going to be, well, the most obvious one is that merge sort sorts, right? And to prove that, we just need to say that given any arbitrary old list, if we merge sort it, it should be sorted. And once again, I'll put a type signature here just to make Haskell pick a better type. So merge sort sorts. Okay, that's a very obvious property, but there's actually another property we'll need, right? In addition to the fact that it should be sorted, well, I could just write a function, a correct implementation of merge sort right now. If that's the only property I need to satisfy, then we're done, right? I just return the empty list, because the empty list is always sorted. But of course, we also want all of the elements of x's to show up in our result, and none of the elements of our result should not have shown up in x's, right? So we want it to be a permutation, once again. So we also have prop merge sort perm, which is that permutation of x's and merge sort x's of type listed integer. Just adding that type signature there once again to give Haskell the hint. Okay, so now my empty list implementation, if I just quick check it, merge sort sorts, sure does. It returns sorted list every time, but it does not return a permutation, right? So what we need to do is actually implement merge sort, and the way we'll do that is by inductive reasoning. So we start out with the empty list. Well, that's just going to be the empty list. Now we also have to deal with another base case. If we have a single element list, that's already sorted as well, so we can just return it. And the reason we need that is if we look at the way split works, if we have a single element, oh, we have a bug here that I forgot to fix. So it wasn't correct after all. But I believe split perm was finding that bug. I just forgot to remove the bug. You know what? I'm not sure of that right now. And we have time, so I'm just going to double check my intuitions there. Yeah, it was finding the bug. I just forgot to fix it. Yes, so when you find bugs, it is important to fix them. Otherwise, there's not much point in finding them. Cool. So now I have the permutation property. And oh yeah, so what I was saying is, if we look at the way split works, we return this single element on the left-hand side. So if merge sort tried to recurse on this case, it would end up infinitely recursing on this left-hand side and never terminating, right? So I need to handle this one as well. And then we have x's. So any old list that is bigger than 0 or 1 elements, so it's 2 or more elements, then we want to first split it into the left and right lists, right? Split x's. And then we want to merge the result of merge sorting the left and merge sorting the right, right? So that is our implementation of merge sort, hopefully. And we can test it with our high-level properties. So split, here we are, merge sort perm and merge sort sorts. Sure does. So now we have established the correctness of our merge sort, but if you don't believe my existing definitions, like I had to write this sorted function and stuff like that, so there's a few things I'm depending on here. We could also do some more properties, like if I merge sort a list of integers, I should also get the same result as if I used the built-in Haskell sort, which I believe is some sort of efficient sort. I don't know exactly. Oh, I typed the wrong equals. It's a double equals. Now if I check my merge sort extra property, merge extra, did I call it? Yeah, I should have called it merge sort extra. I'll just fix that now. So we have all of these properties. And it is true that if we have a program that already satisfies these two, then this one is redundant because it's already a correct sort. But more properties can never hurt, right? So we've got our specification done and we've got our testing done. So we could actually prove the properties of merge sort that we just tested, right? These two properties here, that merge sort sorts and it's a permutation, just as a consequence of the properties that we already tested for split and merge. And the reasoning goes something like this. For permutation at least, in the base cases, we have empty list and one element, which is trivially a permutation, right? So these two are obviously permutations. The output is obviously a permutation of the input. And then in the inductive cases, we know that split returns a permutation of its input, right? L plus plus R is a permutation of x's, and because of the split perm property, and then because of the merge perm property and the inductive hypothesis about merge sort of L and merge sort of R, we can conclude that merge will return a permutation of L and plus plus R. So because of these two properties, merge perm and split perm up here, we already know just by inductive reasoning that merge sort will satisfy merge sort perm. And the same reasoning applies for sorted. The base cases are clearly sorted. And when we use the inductive hypothesis, we know that if we merge two sorted lists, we'll get a sorted list. And with the inductive hypothesis saying L and R when merge sorted will be sorted, we already know that the result will be sorted. So we can do an inductive proof to show these two properties. We don't even need to test them. But of course, having these kinds of integration sort of tests where we test the overall structure of our program after we put it all together can never hurt, and it can help us to make sure our intuitions are as we expect. Okay. So, yeah, in addition to testing our intuitions, they can also be more efficient than the full functional correctness tests, right? If I just quickly run a test case throughout my entire property, like for example, a very easy to check property about sorting would be that the lengths of the lists are the same, right? We can check the lengths of the list just by doing an order n check, right? And that's more efficient than doing a full correctness check to see that the whole thing actually sorts the list, right? And so we could very quickly check to see if the lengths were the same without doing the full-blown test suite. So sometimes you can have these cheap, less reliable or less useful tests that still have value because they are so quick to compute. You can also have fine-grained tests, like if we test an overall composition of several functions together, it may not execute all the code paths we want to test, whereas if I have just one property that does one very specific thing, but manages to test that more thoroughly, then we can get more coverage. And it's just a good sanity check to our intuitions, as I was saying before. And sometimes full functional correctness is not easily computable, but we can do some simpler properties that are easier to test. So these redundant properties include unit tests, right? And I can even write one. I'll write a unit test in QuickCheck right now. It's a property, right? Mergesort unit, and that is mergesort of 3, 2, 1 should be what 1, 2, 3, right? That is itself a unit test, but it is also a quick checkable property. I can write it right now. Mergesort unit. Okay, passed one test. So we've seen many redundant properties of mergesort. In fact, these two properties would be perfect examples of redundant properties. And even these two properties could be classed as redundant in some sense because they are implied by formal proof from the original properties we had about our component functions. Okay. So the next thing I want to show you is test coverage checking. So we need some way to quantitatively measure how good our tests are, right? So if I run my test case, it might say all tests pass, and that feels great, but we don't really know, have we tested everything we should be? So coverage checkers help us to determine if this is actually the case. Have we covered all the cases we should be covering? There's many different types of coverage checking, and some of them are easier to compute than others, right? So one simple example is function coverage. Have we tested every function we've defined, right? If I define 10 functions in my file, do all those functions get executed in my tests? A slightly more fine-grained version of this is entry-exit coverage, where we say if I have a function, f, and that function is called in several places, are all of the places where that function's called tested, right? So that's testing all of the entry and exit points of a particular function. And then there's a more fine-grained version of that where we have statement/expression coverage. So in an imperative language like Java, it would be a statement, but in Haskell it's more like an expression because we don't have statements. And we're saying, are all expressions executed? Do we execute each component of the code in our function? And then there's a more fine-grained or more control flow based version of that where we say, if I have a conditional branch, like if, are both branches of that condition executed? And then there's path coverage, which is computationally very expensive and theoretically uncomputable in some circumstances, where we say, are all possible executions of my program, starting from its initial state, executed, right? So have we exhaustively analyzed every possible behavior of my program? This is very hard to meet. It's very hard to get full coverage of path coverage, and it's also extremely difficult to compute. So most coverage checkers, which don't rely on model checking algorithms, just use these first four methods alone. Okay, so there's a program coverage checker for Haskell called HPC, and it helps us generate these reports that we can view that help us to check our coverage. So for Stack and Cabal, there's two different ways to execute this program coverage thing, but I'll show you on my computer with Stack. Firstly, you do have to compile your program as a binary. You can't just run it in GHCI like I've been doing. So I'm going to write a main function here, and I'm going to use this special keyword called do, which you don't need to worry about for now, but I'm just going to write a bunch of QuickCheck commands in it. So I'm going to say QuickCheck prop mergesort unit. Let's just do mergesort unit, and we'll see if it executes all of our branches. I'm not sure if it will. Let's see if it does. So we're just going to run this one unit test in this particular case. Okay, I'm going to exit GHCI. I'm actually going to start a shell inside my stack environment so that I can just use GHC directly. You can do this if you're using stack as well, if you just want to use GHC directly. Of course, you can use stack directly as well, but there's many ways to execute this. You can consult documentation if you need help. So I'm going to compile with the coverage flag, right? And make it, oh, that's not how you turn on coverage? Or is it enable? Oh, I don't remember. Let me just quickly check that. I didn't put it in my slides, so I have to check it myself. GHC coverage flag. Ah, okay. For GHC's raw invocation like this, you can go fhpc like that. I believe that will work. So now I can run my program. It ran the test case. And there's a bunch of stuff here that's about my slides, but you can see it's created this file here called lec3.tix, right? And if I look inside this file, it's a bunch of stuff. This is not readable to a human, right? What we need to do is generate, a report, and the way we do that is with a tool called HPC. Right, we go HPC report lec3.tix, I believe. Okay, so it gives me a summary here in this report about how much of my code has been covered. 36% expression coverage, 50% Boolean coverage, so that's like condition coverage, 61% of my functions alternatives used, and 26% of my top level declarations are used. So that's function coverage there. So we get more information if we open up the HTML report, which it may not have generated. I can't see it. Maybe I've got to type something else. All right, so we can go HPC markup to get even more information. Oops, not what I meant. There we go. And now, if I open main.hs.html, oops, it's come up on my other screen, so let me just bring it over. Just a moment. Like so. This is pretty small, let's make it bigger. Then it gives me this yellow highlighting for stuff that in my code that I have not executed. Green stuff for stuff that's always been true. And red stuff for stuff that's always been false. So it's natural that otherwise will always be true, because we know that otherwise is just defined to be true, right? So that's not actually alarming. But we can see here that we haven't actually executed all of our program. We never checked sortedness, right? We just checked that it was this particular unit test, so we never ran any of this code. In this case of merge, never got executed, right? So we never executed a merge where the left-hand side was empty. Interesting. Permutation, obviously we never ran that, so it never executed. Was anything else interesting here? Let's see. I can't see anything else interesting, but let's see. I think maybe some of this might change. Some of these cases might change. Like we never ran the empty list case for merge sort, that's pretty bad. If we add more of our QuickCheck properties. So I'm just going to go over there, and I believe I have to exit, reload everything in the REPL, and edit it. Okay, so if I add my more thorough testing for like merge sorts and Mergesort perm. Now it should test a lot more of my code. So if I stack, get me the shell again. There we go. It's just giving me HPC and GHC and stuff like that. Recompile. Now if I run, it's going to run all, run all of my properties. I'll remove the old file. Now it ran all 3 properties, and if I generate my markup and then go back here and refresh, now it's doing that, and indeed all of these cases have now been executed. So that's good, we've covered those missing bits. So this is how coverage checkers can help us to make sure that we're covering all our cases. Good. Okay, so the last thing I want to talk about today is a concept of Haskell's execution model. So we're done with testing for now. And this is called lazy evaluation. So to start with, I'll show you a program. We've got this program here called sum2, and it just adds up all the numbers from 0 to n. So, I mean, it seems pretty innocent. However, if we give this a very large number, it will crash. Now, why will it crash? Well, I can even try it. Ugh. I'm all over the place today. Let's try it by writing it in our code here. Sum2 takes an integer to integer. Sum2 of 0 is 0. Sum2 of n is sum2 of n minus 1 plus n, right? Okay, sum2 of 10,000. Is that big enough? Oh. Let me just load the file. All right, that's fine. 100,000. A million. Is it being smarter than I hoped? If I give it a big enough number, 10 million is taking a while. Well, a billion. Maybe I should have done factorial instead of numbers. Sum. Or maybe the stack frames are just set so high that it's not causing a problem. There we go. Okay, finally. We got a stack overflow. So you may have seen this error in many other programming languages as well, and usually this happens if you have a large amount of recursion. And we can see here that in order to add up to n, we first add up to n minus 1 and then add on n. And because of that, it's going to build up a whole pile of stack frames, in this case, a hell of a lot of them, and then eventually run out of stack space and crash the program. So this is the same problem that you'd encounter in any recursive function in a language like C. Now, we can do something called tail call optimization, which is a fancy term, but all it says is, essentially, if we rewrite our program to look like this, okay, so what's going on here is instead of returning a result, we add on to our running total. So our running total is A, it's called an accumulator. Each time we see an n, we add n onto our accumulator and recurse down to n minus 1. And then once we hit 0, we return our running total. And we start out our running total at 0 to give us our original sum2 function. So this is still going to crash when given a large number. The number would be larger, but it would crash after a larger number, but it would still eventually crash if I gave it a big enough number. This is kind of irritating, because what we expect from tail call optimization is that because the last thing I do in my recursive function is the recursive call, I no longer need that stack frame for when I call the recursive function. So essentially, rather than keep track of what a and n were when I call sum2 prime, each time I call sum2 prime, it may as well just jump straight back to the beginning of the function and overwrite the values of a and n with the new values a plus n and n minus 1, because it no longer cares what a and n used to be. because the last thing I'm doing in this function is sum2 prime. And Haskell does implement this kind of tail call optimization, and many languages that have good support for functional programming implement tail call optimization. In fact, Guy Steele, a famous programming languages academic, proved that you can't have reliable modularity without tail call optimization, and this suggests that certain programming language designers don't know what they're doing. But I will leave my slagging of other programming languages to COMP3141. So in this example, even though we have our tail call optimization in Haskell, it's still crashing, given a large enough number. So in order to see why, I'm going to do a little bit of equational reasoning. Let's just get the editor open. So we don't have our version of the sum2 with the accumulator here, so I'll just quickly write it out. Sum2 prime a n equals sum2 prime a plus n minus 1. So here's our two equations. So let's just try an example. We start out our accumulator at 0, and we're just going to add in the numbers from 0 to 5. And it will be enough to see what's going wrong. So if we look at our equations, we can see 5 is not 0, so we can't apply the first equation, so we have to apply the second. So we get sum2 of 0 plus 5 and 5 minus 1. So I didn't do any evaluation here. Now, in order to check if the second argument is 0, Haskell has to evaluate the second argument 5 minus 1. So we get 0 plus 5, 4. And okay, well now we can see 4 is definitely not 0, so we can recurse around again, and we get 0 plus 5 plus 4, and then 4 minus 1. And then Haskell has to evaluate that 4 minus 1 in order to see that it is not 0, so it will evaluate it to 3. And then we end up with recursing again. We get 0 plus 5 plus 4 plus 3, and then 3 minus 1. And so on. It keeps going. And so on and so on. And you can imagine then that if I had something like sum2 of 0 and 10 billion, right, we would end up with a very large expression being evaluated here. 0 plus 10, well, how many zeros is that? That's 100,000, but even 100,000 is a lot. We would have 0 plus 100,000 plus 99,999 plus 909,998 plus 99,997, and so on and so on and so on, and then like 0, right? And so we can see that it's never evaluating this first argument. It's just leaving it unevaluated. The reason for that is Haskell is what's called lazy evaluated. That means that it will never evaluate anything unless it has to in order to, for example, check that a pattern is satisfied or not, or to check or to print it to the screen, or to send it over a network or something like that. If it doesn't have to compute a certain result, it won't. Now, normally this is actually very useful, and I'll talk about how in a moment. But in some cases, such as this, where we're doing something like a left fold, we can end up with these very large terms here. And this is what's called a space leak. So it's the main drawback of this lazy evaluation method. So lazy evaluation is also called call by need. And this means that they're only evaluated when needed, right? Hence the name. So in this particular example, how could we force Haskell to evaluate this first argument so it doesn't grow too big? Well, there's a few ways to do this. One very cheap and nasty way would be to do something like this. We add an extra case that just is redundant. Technically you don't need it because the second case already handles it, that checks if a is 0. And then in order to check that a is 0, we have to first evaluate it, so Haskell will be forced to do so. This is a bit cheap though, it's a bit silly, and we're introducing a redundant check that you don't actually need. So a better way to do it is to just put a little exclamation mark here. And this says, I know I'm not checking what A is, but I want it to be evaluated anyway for efficiency reasons. And so this is called a bang pattern. And I believe you have to turn on a language extension, although it's a very innocuous one, to use these. But if you're not comfortable with the language extension, or you're using a very old compiler that doesn't support bang patterns, you can also use a primitive operation called seq, S-E-Q, which just says, here I define A prime to be A plus n, and I say A prime seq sum to prime A prime n minus 1, and this seq here is saying, before you do the recursive call, you must evaluate A prime, right? That's what seq does. But I think it's easier and simpler to just use a bang pattern. Right, so why do we have lazy evaluation if it sometimes causes this problem? Well, it enables equational reasoning even when we have partial functions and non-termination. So if you imagine you have a program that could potentially infinite loop, right? In a strictly evaluated programming language, an eager evaluated programming language, like basically any other programming language you would have used, any non-terminating computation anywhere in your code that gets executed will cause the program to crash or not terminate. So it's even if you have a function that could potentially crash or not terminate, with lazy evaluation, if that particular crashing or not terminating code doesn't get executed, then it won't crash and it won't diverge. So we can equationally reason about code even when we have these kinds of nasties, which is quite useful. It also, and this is the big win, it allows us to decompose problems in that bottom-up design kind of approach that we were showing you earlier. So, for example, if I wanted to say minimum is the first element of the sorted list, depending on the implementation of sort, this can actually be order n, right? Comparison-based sorts are at least n log n, but if the sort is able to compute only its first element without computing the rest of the list, which some sorting algorithms can, then when we define minimum as head composed with sort, it will actually give us the minimum element by only computing the first element of the sorted list, and it will ignore all of the rest of the computation that it would have to do for sort. So this allows us to do amazing decompositions of problems. And in this beautiful paper, which I encourage you all to read, it's very simple, very easy to read, called Why Functional Programming Matters, John Hughes demonstrates how we can even do something like alpha-beta pruning from AI, where you generate a tree of all your possible moves and then you prune out all the ones that are no good. You can decompose that problem into generating this very inefficient, very large tree, and then pruning out all of the things that you don't care about. And the cool thing is, because we have lazy evaluation, we never even compute those things we don't care about. We can efficiently implement alpha-beta pruning as the very simple conceptual algorithm we have in our brains. So lazy evaluation is actually really, really good. It's just has a slight drawback when it comes to space leaks. So you have to be careful about those. Okay, so the other thing that lazy evaluation allows us to do is what's called co-recursive or circular programming. And this allows us to generate infinite data structures. So I'll show you some examples of these infinite data structures in a moment, but one of the really cool things about circular programming is it allows you to do something like, in one pass over a list, replace every element of a list with its maximum, right? So you can't go over the list multiple times, so you can't find the maximum of the list and then go over the list and replace each one of them with its maximum. You can do it in one pass using lazy evaluation. And the program looks weird, it looks very confusing, it looks circular almost, as if it should just run as an infinite loop, but it works. It's very cool, and I encourage you to try and figure it out. And if we have time, maybe I'll post, or actually, yeah, what I'll do is I'll post the solution to this in like a week online. So if you can solve the puzzle, that's cool. Try not to Google a solution, you'll probably find it if you Googled it. Okay, so let's look at some infinite data structures just to finish us off. So we can define a list called ones, right? And that list is defined to be a const cell with 1 as the first element, and the tail of the list is ones, right? So we have this infinite list here. Now, you might think, just looking at that definition, that this would infinite loop, right? But this is not actually the case. And I'll show you. So let's just go to our GHCI. If I say ones is 1 followed by ones, and then I tell GHCI to print it out, whoa, we got a lot of ones, right? But I can even use the Haskell function take. Don't know if you've seen take before. It takes the first n elements of the list. So if I take 10 ones, it's going to give me 10 ones, right? So that's kind of cool. We can use filter. We can't use filter yet, that wouldn't be very interesting. We can do map. We could do map times 3 on ones, and it gives me a list of all 3. We can even do something like this. So there's this function called inits, right? And its type is like this. And if I go the inits of, let's say, 1, 2, 3, it gives me the empty list, the list containing 1, the list containing 1 and 2, and then the list containing 1, 2, 3. So it's all the possible prefixes of our list. So if I take the inits of ones, and rather than print them all out, I'm just going to take the first 5 inits of ones. It gives me various lists containing an increasing number of ones, right? So if I then map over this, map sum over this list, then this is going to give me the list of natural numbers, right? If I take 10 naturals, it gives me all the natural numbers. And then I can define the even numbers to be mapping times 2 over the natural numbers. And then I go my even numbers. Well, there's a lot of them, but you can see they're all even, right? And we can even do all sorts of other interesting numerical sequences. We can also define the natural numbers directly, right? We don't have to define them using inits and sum. What we could do is go naturals is 0 is the first natural in computer science, not 1, because we're computer scientists. And then we say map plus 1 on the naturals. So this is a bit confusing. If I spell it out by writing it out here, we've got, oops, my mouse just clicked somewhere. Where is my mouse? There it is. Right. So naturals is 0 followed by map plus 1 of 0 followed by map plus 1 naturals. Let's just have that, which is, if I run this map over this element, that's going to give me 1 followed by map plus 1 naturals. So now you can see this naturals is 0, 1, and so on. And then if I map plus 1 and then map plus 1, that's going to give me 2. And then map plus 1 of 1 is going to be 3, and so on, right? So you can see this is going to give me the natural numbers as well. So if I take the 10 naturals here, I get the first 10 naturals. Now we can even do more complicated ones. Let's try the Fibonacci numbers. So the Fibonacci numbers, if you remember the definition, is 1 is the first Fibonacci number, and then the next one is also 1, and then every subsequent Fibonacci number is the sum of the previous 2. So how can we do that? Well, it's similar to how we did the natural number definition. We say what we want to do is take the list of Fibonacci numbers, which starts with 1, 1, right? And then the list of Fibonacci numbers except for the first one, right? So the one that just starts with this one, and pairwise add them together. So how do we pairwise add them together? There's this function called zipwidth. And zipwidth is kind of like map, except it takes two lists and a function that takes two arguments, or rather takes one argument and returns another function, takes another argument. It's a curried function. So we take in an operator to combine the two lists together, right? So if I, just as an example, if I say zipwidth of plus, and I take 1, 2, 3, and 10, 20, 30, then I get 11, 22, 33, right? So it's just combining these two lists together. So for Fibonacci, because they start with 1 and 1, and then everything is the sum of the previous two, then this is the sum of Fibonacci with tail of fib, right? And if I take the first 10 fibs, it gives me the first 10 Fibonacci numbers. So we can do a lot of very interesting and cool things with lazy evaluation. I've only really scratched the surface here. We'll see a few more examples throughout the course of us making use of lazy evaluation, and sometimes we won't even notice that we're doing it. Because when we reason equationally, we don't need to care about if things are infinite or not, or if things could potentially run forever or not, because we only ever consume the parts of the data structure that we're interested in. So it's a very useful concept to just have in the background. So I encourage you to experiment with this and maybe come up with your own numeric sequences that you can define using lazy evaluation. It's a lot of fun. And there's a lot of fun brain puzzles you can do about lazy evaluation too. Okay, so that's it for today's video lecture. The second exercise has been released along with this video, as well as the next quiz. So make sure you get started on those. And the first programming exercise is due on Wednesday, this Wednesday, not next Wednesday as was originally advertised. And the last quiz from last week is due this Friday. And this quiz, which is just coming up with this video, will be due on the following Friday. So hopefully we're settling into a rhythm now, so everything seems pretty routine. And of course, contact us on Piazza if you have any problems, and we'll be happy to help. Okay, see you in Curtis's lecture on Wednesday.